So what we're going to do in section 9.3 is actually go after solving differential equations. And some of them we can solve in ways that you saw me work in section 9.1. We'll start with this one. dy equals 9x squared y squared. And the goal here is to get an expression for y. So the first thing I'll do is I'll multiply both sides by dx and get dy equals 9x squared y squared dx. So it canceled on the left, and we've got it on the right. Now I want to get all my y's together. So I'll divide both sides by y squared. Now what's going to happen is that eventually you guys are going to get pretty good at going from here down to here, and that's fine. I might do the same thing myself. But divide both sides by y squared, it cancels on the right. We're stuck with it on the left. Well, the nice thing is I've got the variables together. So dy over y squared equals 9x squared dx. And what that allows me to do is to integrate both sides. So let's do that. I'll apply the integral to both sides. On the left-hand side, you might want to rewrite that as y to the negative second dy before you integrate it. The right-hand side, that one just integrates pretty quickly. Add 1 to the exponent, divide by that same exponent. So I'll have an x to the third divided by 3 times the 9. You're only going to put a constant of integration on one side. You can put it on both sides, but don't waste your time. Because if you put it on both sides, you had a C1 and a C2. Move over to the right-hand side, call your new constant C3. But it's still a constant. So we're only going to put a constant on one side. The left-hand side is going to turn into -1 over y equals 3x cubed plus a constant. Except the goal was to solve for y. So I'll start by multiplying both sides by -1. And I'm still not done. I can take the reciprocal on both sides, and kind of the fancy way that I can do that would be just to raise both sides to the negative first power. So that's going to take the reciprocal. That's going to give me a y here, and the negative I'll keep up top, -1 over 3x cubed plus a constant. And there's your solution. That's your solution for y. Beautiful. We'll try a couple more and see some other tricks and things you can do along the way. And I'm hoping that the last problem that we'll do, we'll be doing an orthogonal trajectory. Let's try, boy. You know, I'll do one more of kind of the easy case like this, and then we'll do a couple initial value problems. Not that the initial value problems are like terrifically hard, but they are going to involve a little bit more. So I do want to do a couple of those. Just FYI, I choose problems out of the homework as much as I can. So let's try another one. dy by dx is 5x times the square root of y. So we're going to play the same game that we did with the last one, and that is we're going to multiply both sides by dx to get dy by itself. And then I'm going to want to put the y's on one side and the x's on the other side. So naturally, that means dividing both sides by the square root of y. 5x dx. And let me rewrite that as y to the -1/2 dy equals 5x dx. The good news here is that I've got the y's by themselves and the x's by themselves. So I can integrate both sides. It's nice that we have this notation that comes from Leibniz. So we have the dy and the dx that are our nice differentials, and we're all set up for our integrals. Let's come up here to the right, add 1 to the exponent, divide by that same exponent. It's going to give me y to the +1/2 divided by 1/2. On the right-hand side, that's where I'll put my constant. I'll get 5x to the second divided by 2 plus a constant. Dividing by 1/2 is like multiplying by the reciprocal. So 5x² over 2 plus c. We want to solve for y. So the first thing that I'm going to do is I'm going to divide everything by 2 here. So we'll divide everything by 2. That's going to give me the square root of y equals this divided by 2, which is going to be 5x over 4, plus a constant divided by 2. And I'm not sure if you're going to like this or not, but a constant divided by a constant is a constant. I mean, technically, this is like a C1 and this is a C2, but we're not really going to take that much care in differentiating these things. It's still a constant. What's the last thing I need to do to get y by itself?
Square both sides.
Thank you. Sounded like Alex. Square both sides. Yep. And there's your solution. Now, the problems that we're going to come up against next are going to tell you things like, well, when y equals 0, or when x equals 0, y equals 4, or something like that. And it's going to allow you to solve for that constant. But on these couple, we didn't have to worry about it. So great for us.
And web design, does it take it like that, or do you have to simplify it out?
It should take it like this. Okay. Trying to find a decent one to work our way into these initial value problems with. I don't see one. Let's take a look at y prime tangent of x equals a plus y. So this is a differential equation, and we can separate the variables and solve here, but they also tell us something else, that y of pi over 3 is equal to a. And one last thing that they tell us is that 0 is less than x is less than pi over 2. And that should be a 0 here. Let me fix that. Actually, maybe you can use your telekinetic powers and reach out through the internet over to my page, and 1, 2, 3, well done. Make that a 0. Thank you. All right, so this is your initial condition that at x equal pi over 3, the function equals a. So we're going to have to go back and worry about that after we finish solving. for now, let's work about solving. Let's see. This is dy by dx times the tangent of x equals a plus y. So dy times the tangent of x equals a plus y times dx. If I want to get the y's by themselves and the x's by themselves, I got to move the tangent over here. I got to move the ay over here. So if you don't mind, I'm going to do both of those operations at once. I'm going to divide both sides by tangent of x and a plus y. Tangent of x and a plus y. How does that work for me? Well, pretty good, because my tangent of x term is going to cancel. And on the right-hand side, the a plus y term is likewise going to cancel. So that leaves me with dy over a plus y equals dx over tangent of x. Cool. That's what I wanted. Wanted to get those things separated. So now what? Well, now we're going to integrate dy over a plus y equals the integral of dx over tangent of x, which you might find that a little bit more agreeable to work with in a different way. The reciprocal of the tangent is what? And remember?
Cotangent.
Cotangent, thank you. And cotangent is really cosine of x over sine of x. Now the antiderivative of the cotangent of x is not something that I keep in my head. But if I need to, I can just derive it. On the left-hand side, this is going to integrate to the ln of a plus y. On the right-hand side, well, any suggestions? What could we do?
Substitution. Use substitution.
Yeah, use substitution. You've got two choices. U equals sine of x, U equals cosine of x. Let me just steer you in the right direction. If U equals sine of x, then your du term is cosine of x dx, and that's already in the numerator. If you did it the other way around, yeah, cosine of x derivative is going to be including a sine of x, but that's in the denominator, and you won't have that readily available. So we're going to let u equal sine of x. This is going to integrate to the natural log of the sine of x. ln of the sine of x plus a constant. Okay. Now our goal is to solve for y here. Are we okay with where we're at the moment? How we got here? All right, because I'm putting my previous sheet in the copy pile, and it's not coming back. All right, so we're good. Let's keep going. We want to get the a plus y term by itself. So what I'll do is I'll exponentiate both sides. And e to the ln of sine of x plus c these two things cancel each other out. So I get the absolute value of a plus y. Let's see what happens on the right-hand side. On the right-hand side, I can think of this as e to the ln of the sine of x times e to the c. And I don't know, out of pity for you guys, let me give that a different constant value. Let's just call that a k, even though you just could call it c again if you'd like. We'll call that k times this, k times e to the absolute value of sine of x. Well, originally they told us that x was between 0 and pi, so sine is going to be positive here. I don't need the absolute value anymore. I'm going to get k times sine of x. And likewise, I can get rid of the absolute value over here, because this is guaranteed to be positive. To finish solving for y, I get y equals k times sine of x minus a. Wow, a lot of work to get that. Let me pause here before we go back and solve for our initial value. Actually solve for k. And I know my k's are terrible. They look like h's. Sorry. That's okay. All right, so a little bit of work left to do then. We have to solve for k. For that, we're going to use our initial value. The initial value was that y of pi over 3 was equal to a. So that means if I put in a pi over 3 here for x, I'll get a for y. So let's try that out. Plug this into here and see what we get. So it's going to be a equals k times sine of pi over 3 minus a. After hours of calculus class, I'm not going to bother you for figuring out what this is. I'm going to add a to both sides and get 2a equals k. Sine of k, sine of pi over 3 is going to be square root of 3 over 2. To finish solving here, I'd multiply both sides by the reciprocal. Reciprocal in this case is going to be 2 over the square root of 3. Everything here is going to cancel. On the left-hand side, I'm going to get 4a over square root of 3 is my value for k. And that's a 4a, not a 49. If I put that up into my final answer up here, then I end up with my final solution here, which is y equals 4a over the square root of 3 times sine of x minus a. That's the final solution. Wow. I should take attendance just to find out who's still awake and asleep, not asleep, or who didn't leave the meeting. It's challenging. There's no two ways about it. It's challenging.
So we can leave like the square root 3 at the bottom. We don't have to, you know.
Yeah.
Okay.
Oh my God. If you got here, my inner child would be doing somersaults. I'd be so happy. These are tough. I mean, I don't know.
Yeah, it's tough. No, it's tough.
Yeah, yeah. And then the last thing I'm going to do is ding you for points by not rationalizing the denominator. That'd be so cruel. Oh, no way. So maybe if this was a 1,000-point problem and you didn't rationalize the denominator, I'd take off half a point. But yeah, these are challenging enough. I'm not going to worry about that. And I don't think WebAssign will either. If they do, let me know, and I'll send them a little nasty gram in the mail. Okay, man, just a couple more problems that I need to do. Boy, so much math, so little time. I know your brain's probably mush at this point, but if there's something around all these steps that we did, a lot of it's just your college algebra skills coming back into play to solve for this stuff. If there's something that maybe I went over too fast, please help me out. Ask a question. You're helping out your fellow students too. All right. Let's knock off this one. Orthogonal trajectories. We're going to start out with y squared equals 7k x cubed. And for different values of k, this is going to represent a family of curves. So, great. In fact, I'm going to hold my breath here for a second and see if I can't pop up such a family of curves on WebAssign. So, not WebAssign, decimals. Got WebAssign on the brain too much. Let's do y squared equals 7k x cubed. And I'll let k be a few values. K equals 1, 2, and 3. Okay. So there's a few values, a family of curves, and you can plot tons of these things. Now, what we're interested in is finding something that's perpendicular to these, a family of curves that wherever these things intersect, it's perpendicular. Do you remember what's true about perpendicular lines? How do their slopes match up?
Inverse.
Inverse and reciprocal. Good, thank you. So the first thing I have to do is I have to find the slope of the equation, or slope of the line here. And what tells me the slope of a line is the derivative. So that's going to mean I'm going to have to differentiate this implicitly. So how's that work? Well, back in Calc 1, what I did is that everywhere that there was a y, I wrote it like this. Just to remind you that when you differentiate a term like this, you've got to use the chain rule. So the 2 is going to come out in front. I'm going to differentiate both sides of this with respect to x. The right-hand side, I'm hoping, is not a big problem. The right-hand side is going to be 3 times 7 is 21, times k, which is a constant. This we just differentiated, so you subtract 1 from the exponent. But the left-hand side, a little bit more going on here. Derivative of the outside is going to be 2 times y times the derivative of the inside, which is going to be dy by dx. So you're just applying the chain rule here. Now, before I get too far here solving for things, I'm going to take care of something else here. This k is bothering me. It's annoying me. My initial equation tells me that k, you divide both sides by 7 and x cubed, k equals y squared over 7x cubed. So let me put that in here. So it's going to be 21 times y squared over 7x cubed times x squared. And I can clean this up a little bit. 7 cancels into there 3 times. 2 of these x's are going to cancel. It's going to leave me with 3y squared over what's going to be left? Just x, right? Now, I'm left with 2y dy by dx equals 3y squared over x. My near-term goal is to solve for the derivative here, because the derivative is going to tell me the slope of the tangent line. All right, so what's the last step in solving for the derivative? That would be to divide both sides by 2y, or a different way you can think of doing that is multiply by 1 over 2y on both sides. On the left-hand side, this cancels. On the right-hand side, well, one of the y's will cancel, and I'm left with 3y over 2x. Okay. Beautiful. Looking great. Now, this is the slope of the tangent line to our current curve. Perpendicular lines have slopes that are negative reciprocals. So just a little bit of a reminder here for you. So an example would be like 7 and negative 1/7, or 5 halves and negative 2/5. Those would be examples of slopes that are perpendicular. You have to do 2 operations. You have to take the opposite and the reciprocal. So that's the slope of the tangent line to our current set of curves. If I wanted something perpendicular to that, I've got to take the negative and reciprocal. So it's going to be dy by dx is going to be negative 2x over 3y. That's the negative reciprocal. So this is going to give me something perpendicular to this slope. So perpendicular. And now we're going to finish up by solving this. So solve dy by dx equals negative 2x over 3y. Well, this is a nice proportion. I can just cross multiply. I get 3y dy equals negative 2x dx. Believe it or not, there's good news for you here. This one's mercifully easy to solve from this point. I'll integrate both sides. On the left-hand side, this will integrate as 3y squared over 2. On the right-hand side, it integrates as negative x squared. Remember, we only put the constant on one side. If I wanted to get rid of this constant here underneath here, multiply both sides by 2, I get 3y squared equals negative 2x squared plus a constant. Yes, a constant times a constant is still a constant. If I move this over to the left-hand side, then I get something which looks like an ellipse. And that should be a set of orthogonal trajectories to our initial curve. Whew. All right. So a lot going on with that last one. Let me recap what you're going to have to do. And I think it's the last problem in your homework there on WebAssign. You're going to have to differentiate this implicitly. So we did that. We did that carefully. Drew the outside times drew the inside. I took advantage of the initial relationship to solve for k. So I got rid of the k before solving for dy by dx. You don't want to solve for dy by dx with that k in there. Get rid of it. Once I found the slope of the tangent line, your set of orthogonal trajectories are going to be things that are perpendicular to this. So to get a perpendicular slope, you need to take the negative and the reciprocal. Both of those, which you did. Once we had the negative reciprocal, that gave us a decent equation to solve. We can do that by cross multiplying and then integrating both sides. Look, I would accept this. If you got here, that'd be fine. I cleaned it up a little bit just so that I could see what this would look like. The graph of these equations would be ellipses. You don't have to go that far. Let's see, 3y squared plus 2x squared, oops, squared plus 2x squared equals, okay, there you go. So graph kind of a family of these things by plugging in that k. But if you look, for each of these curves, and let's put in maybe one or two more. There you go. You look at how these curves intersect the red ones, they're meeting at a right angle. So that's what we wanted. We wanted one family of curves that was perpendicular to another family of curves, and that's exactly what we got. So pretty cool. Nice to be able to give a good visual with that. Anything else? I know I've covered a lot. Don't worry about it. I'll give you 5 days to work on it, okay? But unless there's somebody that has something else, then we'll say goodbye. Nothing else?
I don't, it was for the one before, the orthogonal question that we just did. It was just confirming something. I just wanted to make sure. For the dy tan x equals to a plus y dx, we put it over tan x times a plus y because that was the least common denominator.
Yeah, so what I did is I divided both sides by tangent of x and a plus y. I mean, I could have done that in maybe a couple steps. Maybe that would have been better. dy by tangent of x equals a plus y times dx. I could start by dividing both sides by tangent of x. And that would give me dy equals a plus y times dx over tangent of x. And then I could finish by multiplying both sides by 1 over a plus y. And that would give me this down here. So I was perhaps a little too cutesy and simplifying things in one step. Maybe I should have done it in both steps.
That's okay. Thank you. I appreciate it.
Yeah, no problem. Anything else? Okay, let me stop the recording here, and good luck on the